Good morning, ladies and gentlemen, and welcome to the last day of EuCNC and 6G Summit. We will start the day with two keynote talks. 6G is a lot about technology, it's not a lot about regulation. These are the areas that we will have the pleasure of enjoying keynotes today. There are obviously other facets to 6G, but those have been dealt with in other keynotes already earlier in this. But today we will discuss about the physical layer as well as the regulatory aspects of getting into a thriving 6G world. Now, our first keynote will be delivered by Professor Ana Garcia Armada. She is a professor at Universidad Carlos III de Madrid, so UC3M, and she leads the communications research group there. She is an IEEE fellow, vice president of member and global activities of the IEEE Communications Society. She has vast experience in wireless communication as she has coordinated many research projects. She has also been recipient of many awards, including third place in Bell Labs Prize 2014 for shaping the future of information and communications technology. Outstanding Service Award from the IEEE ComSoc for Women in Communications Engineering Standing Committee and IEEE ComSoc KICS Exemplary Global Service Award. She will be talking about towards a 6G physical layer. So Anna, please.
Thank you very much. I think the clicker is here. Thank you very much for the invitation, and thank you all for attending. So I'm going to talk a little bit about my view of how 6G should be. But before going to 6G, let me tell you where I think we stand right now. So I think it's nice to see first what we can do already today with 5G, and then see what we cannot, right? So first I'm going to play a very quick video of a project that we did with my colleagues from Nokia in Madrid, Spain, and it's only a very short one with no sound, just to explain to you a little bit a very nice project that we did with a millimeter wave 5G close to Madrid in a village where there is a nursing room, a nursing home with elderly people that have some degenerative diseases. And you can see how happy they look. They are immersed in the world of their youth, and they are experiencing the music and the ambient. And that was thanks to millimeter wave 5G, new radio, that delivered all the video content to the nursing home. So it was nice because not only we could understand what 5G can deliver and how, but we could also understand how this can be used for the people. But it was, I'm not going to say it was easy, but it was not that difficult because it was fixed, wireless, nobody was moving. We had very few users. We had the whole millimeter waveband for us. And it was not fully immersive, just, virtual video, but nothing else. Now, where would we like to go? And it's not possible today. It's another video that is fake, right? This is not happening yet. But we would like to have a more immersive communication with holographic, perhaps, where we can have interaction with the other people as if they were with us. And maybe you will recognize this movie. We would like a fully immersive experience, including all our senses, not only the vision and, be completely surrounded by whatever we can see. And we would like to interact with many people at the same time and have many simultaneous users. And that's the hardest one. We would like to do it on the move. And they are moving very fast in this video. And they are still, communicating fully immersive all the time. But this we cannot do, right? Because, well, in the movie, this was happening in 2040 something. So maybe even at 6G we don't manage, but for 6G, for sure, we need to achieve this. And there are many challenges. We have a project called My Future, where we have been first understanding what are the main challenges regarding not only the architecture that needs to for sure change a little bit, and also the societal challenges, how we can achieve, what our society is needing in terms of sustainability, in terms of spectrum use. But most importantly, I'm going to talk today about some of the technological challenges. And they are many. I want to mention perhaps the ultra-large MIMO, so scaling up MIMO. What is next after the MIMO that we have today? Of course, I'm going to talk a little bit about sensing and positioning being done jointly with communications. And I think we all have the feeling that reconfigurability maybe is the next step in achieving some degrees of freedom that maybe we cannot reap even with MIMO. Let me tell you a little bit of my view of reconfigurability. We are working a little bit on liquid antennas. And it's called liquid or fluid antenna systems, and now some other people are working on that. Here you see just a very small experiment where with a liquid that is a metal that is liquid at room temperature, it's called EuCNC, you can even move, you can see in the video, you can move the little bit of metal without any mechanical device, because you don't want your phone to have pumps or things like that, but we can move it with the displacement that is achieved by the electromagnetic field. That means we could reconfigure the antenna even just with our signal, have some part of the signal to move the antenna around and another part to really transmit, right? So maybe this is going to achieve in the future the degrees of freedom that we are missing, because if there is blockage, well, what we are not doing today is move the antenna, right, to skip the blockage. We are looking at, well, have diversity here, there, but what if I have my hand here, the antenna moves to turn around, right? Well, I'm not going to talk more about this today, but I wanted to just give you a little bit of my view of what could be the future of reconfigurability, but I'm going to just talk more about the waveform, because all this requires a waveform. Even the liquid antenna, but also energy efficiency, any of these challenges, first of all, we need to define how are we going to transmit our signal. And of course, we need to transmit a signal that is able to comply with the KPIs that are foreseen for 6G. Now I'm going to look at some of them and see how this has an impact on the way we transmit our waveform. So for example, we want higher throughput. We always want higher throughput, right? So this time we want 1 terabit per second, and every user should experience 1 gigabit per second. That's a lot. That's a lot that needs spectrum, because even with MIMO, I mean, these are really very, very high data rates. And if we need a spectrum and we can find spectrum in higher frequencies, that is where spectrum is still available, we need to fight very hard radio frequency impairments. We will have amplifiers that are not efficient. We will have phase noise. We will have all the problems that we got used to more or less compensate in the past in lower frequencies, but they are even worse at higher frequencies. So this has an impact on the waveform. We would like to have end-to-end latency that is very small, less than 1 millisecond. And we would like to move 1,000 kilometers per hour and still, be fully connected. This has an impact on the duration of our symbols. In principle, if you want very low latency and you want to go very fast, you would like short symbols. So the channel doesn't change while you're transmitting. But currently, our view has always been the opposite, right? You wanted large symbols to compensate multipath. And we are still going to have multipath. So also there is this channel variability and how to cope with it. So how to design our pilots, how do you design your signal so it doesn't have inter-carrier interference because of the movement. This is an open question, right? It has an impact on the waveform. We also would like to have localization with very high precision. And we cannot do a separate system to do the localization and sensing and a separate system to do the communication because we just don't have the frequencies. So we need to also think of some kind of waveform or some kind of channel estimation or the whole thing that is going to help us to achieve both simultaneously. And then, of course, the question is, can we still use the same waveform that we are using for 4G and 5G that have been extremely successful, or do you need something else? And then I think we need to think, what is the waveform that we are using? And actually, this is a waveform that we have been using for a long time because of its many advantages. It's OFDM, orthogonal frequency division multiplexing, and we are using it because it has a lot of advantages. It's robust to multipath propagation, and 20 years ago, multipath was seen as a problem, and now I think we even see it as a richness of diversity because we were able to design a way to transmit in this environment. It has a very easy implementation with a fast Fourier transform, so these are probably very interesting advantages, but it has a lot of disadvantages. It is very sensitive to phase noise, to synchronization. It has a huge peak-to-average power ratio that makes amplification complicated. It has out-of-band emissions that you need to filter, otherwise you will have interference in the other channels. So I often wonder, well, despite all these disadvantages, of course we learned how to somehow compensate them, what is the main advantage of OFDM that made it come up to now, and be ubiquitous? You think of any broadband wireless communication system and it is using OFDM. In my opinion, it is the very efficient implementation of the time-frequency grid and the way to be able, in this grid, to use some time domain and frequency domain scheduling. So we found a way to take advantage of the multi-user diversity, and our manufacturers are now experts in doing the scheduling in the time-frequency domain, and they can do great things to accommodate multiple users with multiple needs because we have this time-frequency framework that gives us the waveform, right? And I think this is something we don't want to give up, and manufacturers will not want to give up for sure. So we need to think of ways to keep this, but still, accomplish all the other needs that we have. So, still, the disadvantages are there, and I added another one, that is OFDM is not good if the channel is changing fast. And this is one of the requirements. So let's see what we can do. So I'm going to revisit a few things that we have been, compensating somehow in the past, but some of them maybe were not so important and maybe now became important, or maybe now we learned more and we are able to do things in a different way. So I want to somehow think about, for example, PIPR and how we did with OFDM. So with OFDM, there are techniques to lower a little bit the peak-to-average power ratio, so you have less variability in the signal and you can amplify better. And as you know, in 4G and also 5G became a bit optional, there is the single carrier FDMA or DFT spread OFDM. This is a way to lower the peak-to-average power ratio of the signal that we use in the uplink. But I think this is not enough. At the end of the day, single carrier OFDM is achieving the same PIPR as OFDM with some techniques that have been known for a long time, and probably this is why it became optional in 5G. But there are other ways. There are recently proposed OFDM signals that are really constant envelope, zero PIPR. For example, there is constant envelope OFDM. This was proposed by Proakis maybe 10 years ago, and it's just a small modification of the OFDM. And we recently proposed FM OFDM that it's yet another modification. And you can see here, I don't know if I have the way to point, let me check, yeah, that this is just a couple of things that you need to add to the OFDM, but still, this is in general an OFDM system where what you are going to do is you are going to transmit the OFDM signal either in the phase or in the frequency of the carrier. So at the end you have a carrier, and this is constant envelope. Still, it is constant envelope, but it is OFDM. So you can still do the time domain, frequency domain, scheduling, and everything. We know how to do it. We don't need to change. But, I mean, of course, you need to accommodate to this new kind of signal that has some disadvantages, because nothing comes for free. I think the main disadvantage is that you need to lose a little bit of data rate, a little bit, not half data rate, because the signal needs to be real. So it's like in ADSL, if you're familiar with it. You need to convert your OFDM signal to real before you do this processing, and this needs some hermicity, and you lose a little bit of your data rate. And also you need to think how to estimate the channel, because these few things that you are adding here, add some nonlinearities, and you cannot anymore estimate the channel after them. You need to estimate before, and before means in the time domain, before you do all the frequency processing. Yet, losing half of the bandwidth, if all other impairments are solved, may have some meaning in some particular scenarios. And actually, you can see here how good constant envelope and FM OFDM are regarding the PIPR, because you need 0 backoff. I mean, you don't need to put any backoff, or, well, at the end, maybe you need 2 or 3 dBs, but it's constant envelope, right? As compared to the classical OFDM, or even the DFT spread OFDM that still need a lot of backoff. So if your problem is the amplifier, this is something to consider. Let's talk also about the high mobility, because this is even harder, right? Because the amplifiers, we have been having them for a long time, but the high mobility has really not been achieved. And what can we do with our waveform so it is a little bit more resilient to the channel variabilities? Well, it happens that FM OFDM is very robust to channel variability. By only adding something here, that is cutoff frequency, that means we are going to have a couple of frequencies in the OFDM that we are not going to use, but in our experiments it was only one subcarrier frequency, and by using this processing in the FM, in the frequency modulation domain, this becomes very robust to Doppler and phase noise. Because in this domain of transforming the OFDM to the frequency again, these variabilities get in the lower part of the spectrum, so just with not using a couple of frequencies, you can get rid of these effects. And this cutoff frequency at the end is 1 or 2 frequencies for normal scenarios. So FM OFDM can overcome these phase and frequency impairments without any channel estimation, without anything. Even if you have a flat fading, you don't need to estimate the channel at all. And of course, you not always have flat fading, but with beamforming, the channel and higher frequencies, the channel is getting flatter and flatter. If you don't have a flat fading, you need to estimate the channel. And then you need to think about how to do this, because as I mentioned, it cannot be in the same way as it has been done by now with OFDM. But even if you have no frequency selectivity, but you have a very high speed, this works very well. For example, you can see here FM OFDM with 1,000 kilometers per hour or 250, and even we have some diversity that even speed improves. But this is because we have a flat fading channel. So you don't do anything, and it goes perfectly. And here you can see how it works with phase noise, again, without doing anything. And these are different phase noise masks that are standardized by 3GPP. Depending on what is your carrier frequency, you have higher phase noise if the frequency is very high. But in any case, you see how well it goes as compared to more classical OFDM, where you really need to do something to compensate this phase noise, or, well, even in the channel variations, there's really not much to do unless with classical equalization. We tried also how it can go with non-terrestrial networks, because there are some channel models for non-terrestrial networks, and this is precisely where we're going to have non-linear amplifier, the traveling wave tube amplifier, and 1,000 kilometers per hour. And you know, without any kind of equalization in this channel, the behavior of FM OFDM is very good as compared to OFDM or the DFT spread of the FM, where we added perfect channel state information, and still you don't really know well how to compensate with classical channel compensation these effects. So it has disadvantages, but it looks there are some scenarios where this can be something interesting. But I mentioned the channel estimation, and I mentioned it's not easy. In this case, it's not straightforward. So we need to think also, how do we estimate the channel if we want to do some changes in the OFDM? Because usually, in all the OFDM standards, we use what is called pilot symbol assisted modulation. That is the classical way of putting pilots. You have your time frequency grid where you are going to have all your data, but in some places in the time and frequency, you scatter some pilots, some reference signals that are going to help you understand what happened in the channel there and compensate your whole signal. And this is fine. This is the most frequently used. Usually, when you do this, you do the processing in the frequency domain, but this is not the only way. You can also try to do something else, and actually I mentioned in this new constant envelope FM OFDM, you cannot do the processing in the frequency domain. But there is superimposed training that is a different technique where if you have all your data, for example, in the time frequency, you put pilots all over the place, simultaneously superimposed to the data. And of course, you need to do something, right? You need to cancel the interference of the data over the pilots if you want to estimate the channel. But this can be done, and there is some averaging techniques that take advantage that the data at the end of the day are going to be zero mean. And you can do things that are really not complex. So the question is, can we use this with these new waveforms? And also, maybe these new waveforms have some characteristics that maybe can tell us ideas of how to place the pilots in an efficient way, not necessarily the same way we were placing them in OFDM. So, for example, in constant envelope OFDM, which is an OFDM that goes in the phase, we thought that maybe you could also inject phase shifts that are going to be your pilots. So we put some phase shifts here, and with them, of course, you need to design the phase shifts in a good way and how you are going to use them. But we are able to estimate the channel, so this doesn't have any extra power. It's just on the phase. No extra power for your pilots. There is, of course, a little bit of interference, but if you are able to average somehow, you can get very good results. Actually, if you see the black, is the perfect channel estimation, and we get very, very, very close to the perfect channel estimation for this particular waveform. Just thinking, okay, maybe I put the pilots in the domain where this waveform is working, and they entail very little overhead, no power. And there are other ideas. For example, maybe you are not familiar with this particular waveform, but it is a filtered multi-carrier. 10 years ago, filtered multi-carrier waveforms were very much on fashion. Later, we didn't work much more with them. But they are filtered, so some of them have some spectral characteristics that leave holes, right? So we thought, oh, why don't we put the pilots in these holes? And we did that, right? So we proposed, you can see here, oh, sorry, I clicked the wrong one. You can see here the signal with some pilots just in the place where there is no signal. So they are not going to damage, but this is part of your signal anyway, so you need to transmit this part. We did this some time ago, and now working on FM OFDM, it turns out it has the same spectrum, or very similar. So we can also put pilots somewhere in the spectrum where you have less amount of signal, because these filter signals are not flat like OFDM. So there is opportunities to pour pilots here and there in places where they are not interacting too much with your signal. And this we think is interesting, it's an idea, but we also think we need to reflect on, do we really need always pilots? Why are we transmitting all these reference signals? We are transmitting these reference signals because we do coherent communications. So we have a transmitter that is going to transmit a known signal, a reference signal, we call it pilot, because when it goes through the channel, we're going to receive something, and from what we receive, we are going to understand what happened in the channel, and we are going to compensate on the subsequent signals, right? And this is good, but do we always need to do it this way? We know, because well, it's been a long time and we have learned a lot, right? We know usually this coherent processing gains 3 dB as compared to doing non-coherent. But still, there are places, there are situations where the channel changes very fast, or you have very poor SNR, and we know theoretically from a long time ago that in these cases it's not worth investing in pilots, getting the channel and compensating. So maybe there are situations where you don't want at all to have any pilots. And we have been working a little bit on non-coherent massive MIMO, because in massive MIMO you really have a lot of channels. And it is a very interesting case where maybe it's better in some cases not to estimate at all the channel. There are some works by people from Andrea Goldsmith and her team that studied some kind of amplitude detection that doesn't need any coherent detection. And they show that actually in an asymptotic way, you can, in massive MIMO, you can achieve the same performance with coherent and non-coherent. But of course, asymptotic means infinite number of antennas, right? We have been working in differential PSK that requires a smaller number of antennas, maybe it is a little bit more practical, and we have even been working on how to multiplex several users. This is difficult because when you have multiple antennas, among other things, you want to multiplex several users in the space domain, right? You want to use your antennas to have several users at the same time and frequency, but they are separated in space. But you need channel information to separate them. It's not that obvious to do this without the channel information. But on the other hand, you don't want to put a lot of antennas only for one user, even, of course, if you have the others multiplex in frequency and time. So we have been working on ways to multiplex these users in the constellation domain, and we achieved some constellations that individually are PSK, so you can do this differentially, but jointly you have very interesting designs. Some of them you can come up with them heuristically, but some of them it's just artificial intelligence that gave us some designs because it's not that obvious how to place these users in the constellation. And you can actually achieve things that are reasonable. You can, for example, with 500 antennas today is not science fiction, you can achieve a very good performance with 2 users. I would say the limit today is 4 users. You cannot do more than 4 users simultaneously in time and frequency in these schemes. So this is, you know, if you want something to research, this is a nice topic because it would be interesting to be able to multiplex more than 4, right? In some situations, this is probably interesting. And one may wonder, well, when then shall we estimate the channel and when not? And well, we have been also thinking, can we perhaps use the pilot reference signal scheme of 5G, but replace the pilots by data, or most of the pilots by data that is going to be non-coherently detected, data that is going to be slower data rate than the other, but better than pilots, not wasting your resources. And you can use this data once they are demodulated non-coherently as pilots to estimate the channel. And it turns out it works. And it works, of course, better, like, let's say, in the middle, right? So if you have channels that are extremely good, not moving at all, or moving very slowly, and not very extremely noisy or frequency selective, of course you want to do coherent demodulation. This is the best you can do, right? But if your channel is very, very fast varying or slow, very small SNR or extremely high variations even in frequency, you want to do non-coherent, sorry. And in the middle, you can do something hybrid, where you have maybe some pilots, but not too many, and substitute some of them with non-coherent detection. So just, there are options, and it's usually the case that there is no one single solution for all cases. Now, I think it is interesting, now that I talked about the channel estimation, and I talked about the time frequency grid for the scheduling, I think it is interesting now to rethink, is this the best grid that we can use? Because we want to do also simultaneously sensing and positioning. So you want to do some kind of a radar plus communication thing, and maybe there is a structure that is more adequate to do the sensing. Because in the sensing, you want to know the position of things that's attached to the delay and the speed that's related to the Doppler. So if you transmit in the delay and Doppler domain, this signal is going to give you the characteristics of your environment in terms of delay and Doppler. That means in terms of position and speed of the things that are around you. And this has motivated a lot of research in OTFS, orthogonal time frequency space, which is a 2D modulation technique that carries the information not in the time frequency, but in the delay Doppler, which is another domain. We have, been used to the time frequency domain because we have 20 or 30 years of OFDM, and now we understand it fully, and maybe going to a different domain is not that obvious, but at the end it is a domain. I'm going to show you it's another grid. And because of this, there is now a lot of research on other kind of multi-carrier variants that can do also the processing in the delay Doppler, like ODDM, that's orthogonal delay Doppler modulation. And interestingly enough, there is also a DFT spread OTFS. So also people are thinking how to lower the APR, the peak to average power ratio of the OTFS, because it's also a problem. Of course, this can be, right? If you are very interested in mapping your environment, this can be a solution. At the end of the day, this is not that different from an OFDM, but you need to do something before and after that is going to map a new domain, this domain, the delay Doppler, a new grid, to the time, and then you transmit as usual, and then you do the map, and you have a new domain. And you can do the same things. You can have a grid where you have your data and you need to put pilots, but the problem is this is not orthogonal. So if you put a pilot in one position, it's going to be affected by everything around, because this is not OFDM. Then people are proposing to leave a lot of space around the pilot, but this is not efficient, right? At the end of the day, you transmit pilots and zeros. Zeros are pilots in my mind. I mean, it's not data, right? So you need to think of ways to improve also this channel estimation, even in this new domain. But you can do things. And I mentioned the superimposed training, right? So for example, we have tried to do superimposed training in this OTFS. So then what you do is, in all the grid, you put data and pilots all around. And you need to take some advantage of the characteristic of your data and of your pilots to do some averaging of interference. And you can do that, and actually we have achieved very good performance, much better than other schemes that were doing more sophisticated interference canceling and complex things. So at the end, it is possible. It is possible to achieve a reasonable channel mean square error and a very reasonable bit error rate without leaving all these, zeros around. So you can do things with OTFS, and actually, in my opinion, the best you can do is to map your environment, right? So once you have this channel state information, since it is in the delay Doppler, it's like a radar image of your environment, you can do processing similar to radar to understand if there is something or not, if there is a target or not, similar to the Newman-Pearson strategy that is used in radar detection, right? But it is a little bit complex to define what threshold to say if there is something or there is nothing. So we have tried with a deep neural network to train it to understand if there is or there isn't, and it turns out to work very well. And actually, you can see here, well, this is the proposed and the upper bound, and you achieve almost the same probability of detection, with a little bit of penalty in the false alarm probability in the lower range of SNR, but it is just an example of things that can be done. In my opinion, this delayed Doppler processing is good only for this. Because if it is just because you are worried about the speed or other things, I presented other multi-carrier OFDM waveforms that can work. But this kind of processing that, in my opinion, can be done also with other waveforms, and most likely also with OFDM, just you need to transmit the pilots in the domain where it makes sense. You can do a lot of things. So you can do a lot of things. That's my message, right? You can do a lot of things, and there is no one size fits all. But all these waveforms are very similar. They all share an architecture that is the IFFT FFT, that is the OFDM. Many of them can be still, used in the time frequency grid to do the scheduling. And of course, we need to think of the pilots, the reference signals, that should be distributed in a different way in the time frequency grid or in other grids. But this is just pre-coding, post-coding. It's not very difficult. So I think maybe we should go to more flexible waveforms and pilot structures that allow a few things here and there, optional, depending on what is the situation, if you go in a fast-speed train or not, because the waveform cannot be exactly the same. And maybe you think, well, Anna is asking for too much flexibility. This is difficult. I don't think it is difficult. I think we have a history in Europe, in particular, of adding flexibility to our mobile communication standards that has been, leading the way to where we are. For example, in GPRS, we introduced the coding schemes. Until then, there was no flexibility at all. But then you could have different coding, because depending on the situation, you could have more or less data rate and more or less protection. And in Edge, this was increased with the modulation. You could have two modulation schemes. So in 2G+, we invented the modulation and coding schemes that we have today as granted, right? And they give flexibility. In UMTS, there is the variable spreading factor codes, and for the first time, it was possible to have a lot of different data rates depending on what were the needs of the service, because at that time, we were thinking of services that maybe we don't know, and we need to accommodate services that we don't know. So that was really, really flexible. In LTE, of course, all these modulation and coding schemes are there, but we added the MIMO modes. So you could choose to transmit with diversity or to multiplex, different things, because the environment could be different. And also, at the end of LTE, we managed to define different ways of placing the pilots and add more flexibility to the pilots. At the beginning, they were cell-centric, very rigid pilot schemes or reference signals, but then we moved to user-centric, which allow much more flexibility in the pilot design. And of course, in 5G, we have the numerology. For the first time, we can change the characteristics of OFDM. We can make it bigger, smaller symbols, depending on what you need, but it's still an OFDM. Now, next is, of course, to define a little bit more flexibility. So can we, for example, in the modulation and coding schemes, add some differential PSK, so non-coherent the modulation is possible when it is needed, when it makes sense? Or can we add optional pre-coding, post-coding blocks, so we can, do the DFT spread if needed, or you can do FM, or you can do all these possibilities? Can the reference signals have a little bit more diverse formats, or even be allowed to disappear? I don't think this is very difficult, right? And this is my view for 6G, where I think we can accommodate all these challenging requirements with a wise design of the physical layer. I want to thank, of course, all the colleagues of many projects that have been working with me and will continue working, and I would like to thank all of you for your attention.
Thank you, Anna. Very interesting presentation, and gave, at least for me, some new ideas how to go forward in some issues. Are there any questions in the audience? There is one. Can we have a microphone?
All right, Buenos dias and gracias, Anna. Yeah, my name is Mitch Zheng. I'm with E3 from Taiwan, and I'm also I'm the designated questioners in the EuCNC 2024. Right. So, yeah, thank you for all the summary, because you actually provide a very good summary on all the technology we're having today. But one of my role is that I'm also the vice chair of the Applications Working Group in the Next Generation Alliance in the United States. So one thing I've been trying to do is I also like to see your guidance. It's like how do we gather this technology together, and then what kind of effective way we can try to make them kind of implementable in the future. And the reason I'm thinking is that, number one, if we are seeking the 6G applications through Hollywood, then yeah, it's good to provide a lot of applications, but we also need to think about, they never thought about feasibility, and also maybe, for example, who are going to fund this. So since your activities in a university and also you're active in the community, so I'd like to see some guidance from you. Thank you.
Yeah, I think we need to do joint projects with industry and academia. Actually, the project I showed, Amatista, is an example where we combine knowledge from physical layer radio with people that can really do the applications, so we can understand how to improve the radio, so that, and what these applications require from the radio. Otherwise, you know, we can do more theoretical studies, but at the end of the day, I think it is extremely important to do things that allow you to understand end-to-end. And also because I think it is very enrichment. I mean, I enjoy a lot when I can understand how what I do in the physical layer really at the end of the day translate to something that people smile, right? So I think this is the way, and I think now it's getting more and more multidisciplinary, and we need very multidisciplinary teams, but it's also getting exciting, so thank you for your question.
There was another one there. Are you still wanting to ask? Yes.
Hello, Anna. Thank you for bringing this overview and these ideas. Now, I understand you advocate for more flexibility in the physical layer. Can we connect that to many of the proposals on AI that have been put there? Because I think some people have suggested even letting AI define the waveform. How do you see this could reinforce each other? Because what you propose in a way still is careful compared to letting AI propose the waveform. And do you think AI could ever come to the same kind of proposals that you can bring, having expertise on phase noise and other things?
Thank you. This is a very interesting question. I really don't think we are going to substitute the physical layer by a single AI, but I think AI is a very powerful tool to improve some of the processes that we have in the physical layer. Why I say that? Because we need it to be explainable, and we need to understand what is happening, and we need people to trust. And if you put a black box, this is not going to happen. But there is a lot of work in this physical-inspired or model-based AI, and we have also projects on that, where it is not the whole physical layer, but maybe some algorithms that you replace by artificial intelligence because it can be more efficient. And then I see a lot of, and maybe the modulation could be, you could choose the modulation based on some AI, but I think, especially in the physical layer, I think we need to give hints to the AI, because this is very complex, and also we know a lot. So you can tell the machine to learn between several things, but if you tell the machine to learn without any kind of hint, I think it is really complex, and also unpredictable, non-trustable, so I really think we will have parts of AI in the physical layer, but not the whole thing. This is my view. But it is flexible, again, as you say, right? So flexibility to accommodate even some small changes that maybe the machine can do and you didn't foresee. I'm sure. So as you say, I'm a little bit more cautious than maybe, but I think this is at least the near future. Yes.
I was involved in OFDMA for 1997 when I put it in standard, as you know. When I did it, I didn't talk only about space frequency, but it was time frequency, but it was time frequency and space. Each beam, its allocation can multiply the capacity accordingly. About AI, I believe we can go with AI for the physical machine. And the only thing that we have to accommodate is a kind of baseline for a common air interface. When users reaching the cell, we can download to them what is important for this cell, this environment, the new type of correction of software, and then they can run more optimally to the area of the cell, dynamic, everything, and continue with that. So this part might be even not standardized in the future, and we can grow as the AI will learn more and more, and we don't need to wait 10 years for that standardization every time. That's my view.
Yeah, thank you. I think there are different views, and at the moment, all we can do is say what we believe, right? We will see in 10 years where we are, and maybe you are right. I am a little bit more skeptical on how fast we can go in this process, but well, we will see. Anyway, it's going to be a revolution in any way, even with a lot of AI or with a little bit of AI. I'm sure we are witnessing a real revolution in communications, but let's see how fast. Thank you for your comment.
I have one more question. You were targeting these different multiplexing methodologies with these add-ons to different kind of problems, one dealing with PAPR, one dealing with the integrated communication and sensing. Now, we have many customers to one Keynote B. Do you think that you can multiplex these different technologies in the same time frequency matrix?
Some of them, yes. Yeah, I would say some of it. Actually, I was thinking about that, to have some parts of the signal where maybe you put your pilots in the delay Doppler because you want to do sensing, but the other part you want to do more traditional. I have not tried, but I'm sure you can do this, and actually we are working in this direction because I think maybe this OTFS is too complicated, and I think you can reap most of the benefits with your normal OFDM, just designing the pilots in a different way. So I believe you can do something like that.
Okay, excellent. I believe we will give you some tokens of your as an appreciation for you. Here is something that you can put on your wall.
Nice. It's not anymore a surprise because we are expecting the beer. Otherwise, I wouldn't have been doing something.
So, let's continue the session with the second keynote of today. This keynote will be given by Stefaan Vyverman. I hope I pronounced your name. Thank you. Stefaan is the executive director at BIPT, which is a Belgian telecom regulator, where he's responsible for market analysis and attribution of scarce resources. Before, he was the head of 5G launch for the Benelux with Capgemini Invent and wholesale director at Proximus. He has 30 years of telecom experience, and he is excited in innovation networks and new telco technologies. So, Stefaan, the floor is yours.
Yes, good morning. And now it's time for something completely different. I will give you some more insights on the, perhaps for you, less obvious things, and let's call it the less technical elements of 5G deployment, and what this can imply for the future 6G deployment. So, as already said, I stand here before you as a telecom regulator, and perhaps then as someone who is, whose role is more perceived as a necessary hurdle to overcome, or even as a hindering factor for all your numerous technical opportunities that you see, and for all the innovations that you guys all invent. Nevertheless, it's my hope that with this presentation, I can somewhat overcome this perception, and that you also will see us, regulators, also as a valuable partner in the ecosystem, so that we also can contribute together. After all, the regulators, we are, figuratively speaking, we are the suppliers of your fundamental resource for mobile technology, the spectrum. But at the same time, we as regulators, we also need to evolve. We need to evolve. Our regulatory frameworks need to evolve to make sure that we can anticipate on your innovations, and that we really are not blocking for what's coming over the next decades. Now, as a regulator, we have several objectives that we have to meet. And these objectives are actually the basis of our thinking and acting. They are, let's say, they are our raison d'être. These objectives are promoting and ensuring a durable competition. We have to make sure that we develop a strong internal market. The interests of the end users are very important for us. Of course, we are responsible for the management of the scarce resources, and that's mainly the spectrum, but also numbering is a part of that. And also a very important element is the security of the infrastructures. And at the end, all of this, we need to be able to control this and to impose if necessary. But now, on the cusp of the 6G era, I think it's a very good moment to reflect on the journey we have taken with the 5G deployment, and to see this deployment in combination with the objectives that we have set forward. And to now make sure that we see that what the lessons that we learn here, how they will impact what we can do for 6G, and if possible, to do it better with 6G, because it was not perfect. Let's all be honest. And that's also something the regulators have to take on themselves also. First of all, regarding the management of spectrum, the European Commission has launched a very nice white paper some months ago on how to master Europe's digital infrastructure needs. We have a lot of comments on it, I can assure you. But one of the main comments is on the spectrum management, where the European Commission advocates for transferring this authority to them. However, even at this point, the European Commission is already in charge of harmonization, and they are already setting deadlines on implementation. And so we, as Belgian regulator, we do not believe that the European Commission is better placed to do this instead of the member countries, because we also need to take into account specific circumstances for each country that are applicable. The Belgian 5G auction was, as in many other countries, a success, especially when we look at it from the side of the earnings there was for our government. We held that action in the summer of 2022, and with that we were one of the last countries in Europe to do so. Now, the main reason why it was so late, because at that moment we don't have a government who had to approve the regulatory framework for it. Now, one of the advantages for having such a late auction was actually that we had the time to have a broad discussion to pave the way actually to have a fourth mobile operator in Belgium. It makes us a little bit exceptional because there are not a lot of new mobile entries, I think, on the market. Of course, I think it can be criticized whether such a significant difference in timing for the auctions all over Europe, as you can see, it's spanning over several years, if that's an optimal approach. And personally, I think we really should consider how this timing for actions and the related rollout of those new technologies can be organized within a shorter time frame. Of course, always taking into account specific circumstances in each country. Now, in addition to the 5G auction for public spectrum, we also have provided private spectrum in the 3.8 to the 4.2 gigahertz band. And with this, of course, we aligned ourselves with similar approaches in many other countries. The bands could differ a little bit, but I think the approach is in many countries the same. Now, for this private spectrum, although initially there was a big demand from the industry, we see only a limited interest in this offering. In fact, at this moment, we only have 2 companies in Belgium who have signed up for this. In Germany, for instance, there we now see about 100 reservations, but not all of them already activated. Now, and just to put things a little bit in perspective, I learned 2 days ago here on the conference that in China they already have 22,000 licenses provided. So there's a little bit imbalance here. But nevertheless, here in Belgium, and I think also in Europe, we have the impression that several companies first want to build confidence in 5G technology by using private networks that are provided by the public operators. And then eventually, when they have built that trust, then they can consider to move to their own private spectrum. But in each case, what we have to see is the use of this private spectrum remains only for a very limited group of companies who really have the scale and the expertise to integrate telecom activities within their operations. So it is creating a debate within the regulators, if it might be desirable to make the spectrum also available to public operators, as at this point, I think they are using these frequencies more effective than just offering the private spectrum. Now, we also conducted a market inquiry for the 26 gigahertz spectrum. That inquiry revealed a limited interest in that spectrum, and that only would start as of 2025, 2026. The primary use cases that were highlighted there were fixed wireless access, additional temporary capacity, and specific industrial applications that require low latency and high bandwidth. Now, also there, as we follow the footsteps of other countries, we will do a market consultation so that by the end of the year, this band can become available also in Belgium. But even then, while awaiting the final allocation, I think it's important that you all know we already offer test spectrum in these bands for specific tests. And now I have to come back to the mobile coverage. Belgium, As you all know, it's a small country. We are very well covered by mobile networks. As for 5G, we currently see a coverage rate, depending on the operator, between 80 to 95% of the population. And I have to say, these figures, only after 2 years after the auction, I think are a good result. However, what we see is the last percentage towards full coverage. Those are, of course, the most difficult ones to overcome. Now, if I look at our coverage and quality measurements, these reveal really challenges in the transition to 5G. We note a decline in quality of existing networks, of the 2G, 3G, and 4G networks, because, of course, most of the network investments are shifting to 5G. Now, in the areas where 5G has been deployed, that's not a problem, because there the quality is actually more than overcompensated. But what we do see is that from the Belgian customers, at this moment, only 27% have an active 5G device. So this implies that the majority of mobile customers at this moment experience a poorer mobile telecom experience, while they are waiting, first of all, on a full rollout and a full coverage of 5G, but also on the purchase of a new device that is compatible with 5G. And now, at the same time, we still see significant coverage gaps, particularly, of course, in rural areas, but especially on the secondary train lines that we have. We launched a support program there that was worth several millions of euros to help the operators to fill these gaps. But what we had to see is that actually none of the Belgian operators subscribed to that program. Now, to be honest, that's a development that gives some concerns to the regulator and that really highlight the need for more guidance and monitoring in the future for transition to new technologies. And then, another important concern, of course, are the economics around 5G. We've done a study in 2020 to forecast the data usage for the next 20 years. I don't know if it's 100% correct, but it gives a good direction, I think, on where we are heading. As you can see, the data volumes are expected to significantly increase, as well for consumers as for industrial and B2B applications. For consumers, we see a normal growth trajectory, but with business applications where an entirely new market has to be created, we see really an explosion of data at the moment. In our study, we anticipated a take-up of these volumes from 2025. And of course, now we have to wait if this ramp-up in the business segment will effectively materialize. Now, in the same study, we also attempted to predict the revenues that were linked to those data volumes. And they clearly indicate that the additional income that it must come from the new B2B segment. And of course, there's new income needed because the billions that are invested need to be gained somewhere. So the uptick in the business segment will indeed determine the success or the failure of the operator's business plans. However, we still observe businesses are at this moment hesitating to fully embrace the 5G. This is because investing in 5G for a company still represents a significant financial commitment, and in many cases, Wi-Fi remains a cheaper alternative. Moreover, many companies still need to build confidence in 5G technology before making their operations dependent on 5G. Now, how we see it, the best way to promote acceptance of 5G is by demonstrating its value. And this can be done by developing possible examples and use cases that are widely visible and by also effectively calculating the value of these use cases. So we really need to go further than the narrative around 5G, that it's faster, it's better, it's more reliable, and it's also, we see already a little bit for 6G. No, we need to go one step further, and we really need to show the money on the decision makers and in the boardrooms, so they really can take the decision to go to 5G, as there is their real importance for them, of course. Now, the slow uptake of 5G in the industry causes that operators are not yet focusing on 6G, and they are currently primarily focused on making their investments profitable. And as already said, Belgium is a little bit even more specific, because we are here with a new fourth operator who will enter on the market and who will likely extend the payback period for the operators. But nevertheless, I can each country advise to launch a new entry in the market, because what we see is that even if the fourth operator will only get on the market in August, September, all operators are already changing their price schemes, competition is living up again, so it's creating a new dynamic on the market, and that, as a regulator, we can only applaud. The BIPT and other governmental instances have heavily invested in raising awareness of 5G with communication campaigns, a dedicated website, and by initiating demonstrating projects. And now I want 30 seconds for a promotional break. We have a new call for 5G projects within the industry with a budget of 11 million euros. The deadline for submission is 30th of June. So Johan, please start writing and applying for it. All details can be found, of course, on bipt.be. Now, it are not only the businesses who have questions around 5G. Also, among citizens, we have noticed hesitation regarding new technologies. In the beginning, there were numerous myths and concerns around 5G and the fears for health risk. It was the cause of COVID, of course, the 5G. It's normal that birds drop dead, as people said, but okay, these were the fake stories, but we had to overcome these stories, of course. And the combination of all of this has led in several countries to lower radiation standards for mobile antennas. Belgium is a champion in it. I think we have the lowest standards. But also in Italy, Slovenia, Switzerland, and Greece, there are lower radiation standards. And of course, this is causing that deployment becomes more difficult and more expensive. Even at this moment, the Belgian government has taken the position that they will not attribute 26 gigahertz spectrum without additional studies that prove the absence of health risks. So please consider this also as a call for action and start doing studies around this so that we can nevertheless offer that spectrum. Another important part was the network security. There, the European Commission has, I think, really helped us with the 5G toolbox. And we have really implemented the guidelines of that toolbox very strictly, which has led to the exclusion of certain vendors in the active network elements of the operators, and this as well in the core as in the RAN network. Belgium is actually one of the only countries to go so far in the 5G toolbox implementation, but the government has chosen to avoid every risks, knowing that we have headquarters here like the European Union and like NATO. But now, what does this actually mean for 6G? Well, you are all here together to draft the outlines of what the future 6G network will look like. And based on all elements I've told you before, I would like to propose some key building blocks, and a conceptual development that we should approach here all with an open mind. Of course, the foundation of all activities is the spectrum, which is currently already being discussed and coordinated. We are already reserving bands between the 470 and 694 megahertz. We are also doing that in the upper 6 gigahertz band, the 40 gigahertz band, and also above the 100 gigahertz. At the same time, it's essential to ensure that all the technologies continue to function well. So this also means that we will have to find a modus vivendi with Wi-Fi in the upper 6 gigahertz band. Now, at the general technical level, on top of elements that are ready for partly integrated into 5G, such as cloudification and virtualization, I see two major building blocks that should be embedded in the DNA of 6G. It's artificial intelligence and sustainability. And I noticed these were already the subject of multiple sessions here also at the conference. For artificial intelligence, we will not only enhance user experience, but we will also improve the efficiency of 5G through intelligent network management and predictive maintenance. Of course, and it's already said also, this artificial intelligence needs to be implemented within a controllable and a contained framework. As for sustainability, also this must be at the core of the 6G development and also to drive the acceptance, of course, of this technology. The environmental impact of expanding networks and deploying new infrastructure cannot be overlooked. With 6G, we can reduce carbon footprint, we can prioritize energy efficiency, we will have renewable energy resources, we should use eco-friendly materials, and I hope we will be able to optimize the data transmission management. And of course, all these technical elements need to be embedded in the highest standards of security and network resilience. But these are the technical components. We also have some non-technical components that will need to be taken into account. The first one is to have viable and realistic economics around 5G. I already said it before, operators are currently focused on recouping their 5G investments, primarily now by targeting the enterprise segment. Now, the promised potential of 5G must be tapped into and proven before there will be a credible foundation to consider future 6G investments. They really need to see that there's a demand for this. Now, in the development of 6G, attention must be given from the outset to the business plans and the various use cases. And these plans must be thoroughly quantified, and as already said, they have to go beyond the better, faster, and more discourse that was used earlier. It's only with such an approach that we will enhance the economic credibility of 6G. Another important component is to have collaborative ecosystems. With 5G, it became clear that the technology extended beyond the boundaries of traditional telecom actors, and the efficient use cases required involvement of IT, other technology stakeholders, and to have really an end-to-end development. And that's also a little bit the reason why, even at this point, telecom operators are struggling with 5G to sell it, because they are still selling a telecom product. And it's not more a telecom product versus the industry. It's an end-to-end solution they have to sell, and they are not used to that, so they have to grow in that role. But what we see is the formation of ecosystems was initiated far too late with 5G, and we still see 5G, we still see gaps in that development at the moment. So let's not make the same mistake for 6G, because with 6G, we will need unprecedented levels of collaboration across sectors. And from the outset, all stakeholders in the future 6G ecosystem must be involved in that conceptual development. In Belgium, we have taken a very first modest step in this direction with a project that aims to map all current activities surrounding 6G, and to align academic institutions and industry so they have a common prioritization. In the Netherlands, they have invested 100 times already much more into this, so they are already more involved in 6G than Belgium, but I hope with the next government we will be able to catch up. Now, a last component that we see is communication. The rollout of 5G, as already said, has sparked significant resistance due to potential health risks, and with 6G, we will have more antennas, higher frequencies, and this resistance is also likely to intensify. Therefore, again, objective studies on health and other risks need to be conducted, and this not only in laboratory environments, but also in real-life conditions that allow an objective and transparent debate. We need fact-based data to facilitate a real societal discussion on this matter. And simultaneously, of course, the potential of the new technology of 6G must be clearly explained through proactive communication, and it's only that way that we will go to a better acceptation, I think, of 6G. Now, as mentioned at the beginning of this presentation, regulators have a role to play. And the regulators are expected to collaborate to achieve the highest possible standardization and harmonization of both technologies and spectrum. But in addition, you also can expect from regulators that we act as facilitators of innovation who can bring ecosystems together and also to guide them forward. On top, it's also our duty to provide certainty to the stakeholders by designing stable regulatory frameworks. And to achieve this, we need to collaborate with all stakeholders to develop a forward-thinking approach also to regulation. And to be honest, that's something we are not used to do. So it's also for us a huge innovation. But we have to make sure, and we have to be prepared for technology changes that, who are really able to support innovation, and we have to be able to anticipate what comes ahead. I think we have some tools to do that. One of them could be a kind of regulatory sandboxing, or even foresee temporary zones with relaxed regulation to see how things are moving there and what are the results of that. And of course, we also will provide test spectrum, and if necessary, make teams available for advice to whoever has questions around the regulatory framework or already has an input on how it should evolve. Now, I would also like to make a more personal observation by, again, what I see in the 5G, where I think that all public entities and administrations also should become frontrunners in innovation, and also should implement 5G use cases, and already should look to 6G use cases. Because at this moment, regulators and also other administrations are very good to say what others should do. They should innovate, they should invest, but at the same time, we are standing a little bit at the side and are looking into it. But we also have a critical mass that really can spark also the energy and that can create a dynamism. So I would say we also have to jump into the action and really act as an example. So this brings me to the end of the presentation. I hope I have a little bit succeeded to demonstrate our willingness to actively participate in the 6G development. And I hope you are convinced that regulators really can be considered as constructive partners for 6G. And thank you for your attention.
Thank you, Stefaan. Now it's time for questions. Do we have questions in the audience? Toon. There's Toon first and then here Mikko. Well, let's go this way. Okay, Mikko, go ahead.
Yeah, thank you for a nice presentation with good views of understanding the regulatory perspective, and thanks for bringing like our feet to the ground from the 6G clouds. Yes, there is a lot to do still with 5G and these monetization problems we are facing. However, the start of 5G has been faster than any cellular generation before. And one thing blocking of getting the full benefits has been then some lack in the installation of the fully standalone. So there has been the non-standalone approach. And then in this with respect to this monetization in your graphs, you were showing nice growth opportunities with 5G, and I guess that why 6G was not included there is mainly due to that 6G is so far so abstract that it's maybe difficult to more difficult to put numbers there. My actual question comes with this spectrum part of your presentation. For example, at this event, there has been quite some discussion on spectrum sharing and increased importance of that with respect to 6G. So any views from the regulatory perspective in Belgium on spectrum sharing?
Well, actually, spectrum sharing, it's a difficult one. There are some doubts if it's allowed for the moment or not, but I think even now already spectrum sharing is possible within the regulatory framework. Now, we don't promote it, let's say it like that, but it is already possible. If it's requested, I don't think we even have a legal basis to refuse it. So, and in the future, I think we need to create a more transparent framework around this to make it possible. Huh? It's clear.
Then,
My name is Toon Harp from TNO. Can you share some experience within 5G on the resource allocation to uplink and downlink, and some ideas on how to make this more flexible in 6G from a regulatory framework?
I don't really understand your question. Can you?
Well, if you have, for instance, in the public networks, there's a certain division between resources that are used for uplink and for downlink. Yeah. And that is generally geared to more downlink and less uplink. Now, if you have a private network that sits next door in frequency spectrum, you need to often adhere because of interference to the same up and downlink, whereas in these networks maybe they want more uplink and less downlink.
Well, I think we have the necessary safeguards within our spectrum management. So interferences are not really possible. Now, to be honest, on the difference between uplink and downlink, I'm not the expert on that. I have very smart people who are managing that. But I can imagine that it will shift in the future. So the balance between uplink and downlink, and it certainly we have to take into account. But I'm not the expert, as I said. So yeah.
there is yet here in front.
Yeah, thank you. My name is Mitchison with E3. I'm also active in the US standardization part as well. And since we're talking about regulatory related matters, and one thing that I'd like to commentate, I mean, just a comment on that, I think Europe is actually kind of heading a lot of part of the world on this part. For example, over the past few years, GDPR, right, privacy protection, and then we have this cybersecurity and there's a green. Those are very kind of ahead of the world. But now actually there's a new kid on the block, AI, right, AI. So now actually when we in the 6G, we talk about AI native network, and so these days we have AI almost everywhere. But then I think there's another question that people also lingering, that is, so do we allow AI to make decision for human? Or to what degree do we allow AI to help make decision? So I wonder if you have some view on this one. Thank you.
Well, as you know, in Europe we have the AI Act in the meantime. Now this AI Act is more, I would say, end-user oriented to make sure that the ethics are well reserved and that privacy is ensured. The AI we are talking here is more within the technical part. And to be honest, I think we should encourage it. Of course, like I already said, it should be controllable and it should be transparent. So one way or another, we have to make sure that AI does not become a black box, but where we can, I think we should use it. And that's a difficult border to find, but from our side, you will never hear, I think, that we are against AI, certainly not.
Regarding the radiation that you spoke before, that people are worried about that, it is correlated almost directly with the power consumption as well. And the answer to the people that tell you that are not going to give you more spectrum is that if you give me more spectrum, I will reduce my radiation and I will reduce my power consumption, since we have a very famous formula, the Shannon, which said if you give me 4 times the bandwidth linearly, I will increase the capacity. But on the same page, if I will try to do that in partial of the bandwidth, that is going with the log of the SNR. So in other words, if I have a certain bandwidth, give me 4 times the bandwidth, for example, I will transmit maybe 4 times as much power. But if I will try to go to 56 QAM, currently today, we are not fulfilling the Shannon theory. You require almost 64 times as much power, because from QPSK to 56 QAM, it is almost 18 dB in the standard difference.
Yeah.
So it's easy answer. Just use it and ask the regulator to help us.
Okay, I'll take it with me, thank you.
Okay, further questions? Yeah. Okay, there.
The end.
Thank you. Very interesting talk, Joachim Sachs from Ericsson. So I have a question on this commercializations that you touched upon with your study. So the return being, or the market being flattish, the data growth that you see, and that potential is in getting an increasing market in the enterprise segment there. But what is it that you see from a regulatory perspective that you can do to really encourage investments in build-out of infrastructure? I mean, you said something that you want to help the ecosystems to meet, but what are the concrete actions that you see from your role in helping with that?
Well, to be honest, I think we profounded the basis. The industry itself said they were interested. I think it's now on the industry to invest in it. We only can facilitate, we can give communication around it, but the action itself has to come from the industry, from the operators, from the vendors, and they need to convince their customers to really step into this. We can support it, but I think it's not on a regulator to really say, and now this is your direction. We can guide them, but we are not at the steering wheel here. It's a commercial process that needs to be supported, and something that has to come from the operators. So we can facilitate where it's possible. We will give private spectrum. If it's necessary, we can give higher bandwidths, perhaps. That's always to be foreseen. But the investment itself has to come from the industry, and the effort for selling has to come also from the operators. It's not our role to intervene in that process.
Right. So thanks for the reply. But so this basically means that you want to incentivize this by not being kind of a burden also in the process, right? Okay.
At least we will not hinder it. I think that's already an important step.
Okay, one more question, Toon.
Maybe this time not on the radio, but more on the cloud or network side. We see that 6G is going to be cloud native for its implementation. It's going to provide all kinds of cloud-based services, compute as a service. Is there any regulatory ideas on cloud and what to do there? Sovereignty of clouds?
Well, the European Commission now has clearly launched a position on that. So there certainly will have to be control on it so that they not become also too big to fail. That's an important one. We have to make sure that it remains controllable. But for the rest, I would say let the market play. And we'll see what happens. If it really is not longer acceptable, we have to intervene. But we like to see market dynamics also, to be honest. Let the market play. We are not here to regulate everything that we can regulate.
All right, I have one more question. You left the sustainability out of your regulatory framework as part of technical work. In practice, it has seemed to be a really hard nut to crack. We don't have, after 5-6 years of 6G research, even though it was brought on board in a very early stage, in practice, no indicators other than energy consumption for this. Do you think that at some point a regulator needs to step in and say, hey guys, we need this and this kind of performance from your system to be sustainable?
Well, let's be honest, at this moment, I have no power to impose sustainability. That's not within the regulator's power. However, governments also have something to say here, and it's a subject that is living, and it will not go away. Let's be very clear on this. And if it's not happening automatically, I'm convinced one day or another, governments will impose it. So we cannot avoid it. We have to go forward in it, even if it's difficult. But if it was easy, I think we would not be here all to discuss the issues. So.
Okay, thank you very much. And as a token of our appreciation, I will also give you some gifts.
Thank you.
Thank you very much.
Thank you.
Okay, this concludes the session, and we will continue with the panel in half an hour.